Okay, for this problem, I chose to do problem F10-5, which states determine the moment of inertia of the beam's cross-sectional area about the centroid x and y axes. Right here is the original figure. I tried my best to draw it in 3D, but that's hard. First step I took into solving this problem was to state my I, which is b cubed times your height, that's your base, over 12, and my d is from the axis to the centroid. So right here is the same figure here, just redrawn, showing my centroid points and labeling my figure 1, 2, and 3. So right here is the table to solve for the x axis, where I'm going to get on figure 1 for my base 450, where it's this combined, times the 50, which is your width here, over 12. My area is going to be that 50 times 450. There's 0 on my dx from my axis of centroid, and since you have 80 squared x right here, it's still going to be 0. It's actually going to be 0 all the way down, as you'll see here in a sec. Figure 2, it's going to be 50 cubed times the 150, which is its width, over 12. For the area, it's just going to be 50 times 150. And if you notice, your Ix and area are real similar because it's the same on the top, except you're going to have your base always cubed. Same for figure 3. It's going to be the same for figure 2. So 2 and 3 are the same in this scenario. And your dx is still going to be 0. I went ahead and used my calculator to sum it up just right here because I didn't want to have just a bunch of mess right here. So for summing of the Ix, you get 3.828 times 10 to the 8th. And for the area, it's 3.75 times 10 to the 4. Then we know to solve for the moment of inertia of x, so Ix, we're going to have the summation of your Ix here plus the summation of your a d squared x. So if you take your 3.828 times 10 to 8 and add it to your 3.75 times 10 to the 4, you'll end up with this monstrosity, which is 382.83750 millimeters the fourth. Once simplifying down to 3 sig figs, you get 3.83 times 10 to the 8 millimeters the fourth. You can then do the same steps you did from above for the y-axis. So your IY for figure 1 is going to be your 50 cubed times your 450 over 12. And the same as I stated above, your Ix top numerator is going to be the same right here, just you're dropping the cube, so it's going to be 50 times 450. And you have on your y, it doesn't deviate from the centroid point, so it's going to be 0. Your 80 y squared is also going to be 0. For 2 and 3, they're going to be the same for your IY, where it's 150 cubed times 50 over 12. And so the same for your area, but they'll diverge when it comes to your dy, because for figure 2, you're going to have negative 75 from your x-axis, and we know it's going to be 25 up. So your negative 25 minus 75 for 2, and then for your 3, it's going to be the positive version of that. So 25 plus 75. Yet, when you solve it, since it's squared on the end for your dy here, for 80y squared, you're going to get the same answer, where it's 7.500 times 10 to the 7th. And I, yet again, did what I did right here, where I just went ahead and summed it using my calculator. And I got 3.281 times 7 for the IY, and 3.750 times 10 to the 4th for my area. dy, don't know why I did that, honestly. Then my 80y I summed right here, where it's going to be this your 7.50 times 10 to the 7th, basically squared again. And I simplified it down to just 4 sig figs, which is 1.500 times 10 to the 8th. We can use the same step as above for the ix to solve for iy, which is take the summation of iy plus the summation of 80 squared y, where it's going to be 3.281 times 10 to the 7th plus 1.500 times 10 to the 8th. You'll get this big number here, which is 182810000 millimeters fourth. Simplifying that down to 3 sig figs, you'll end up with 1.83 times 10 to the 8th for your moment of inertia on y.